You can eat all the grass-fed beef in the world, but if you're over 65 and missing just one specific molar, your body might not absorb a single drop of vitamin B12. Here is the hidden mechanical chain of digestion. This is what happens inside your body when you lose a single tooth, and why that loss can quietly trigger a chain reaction that reaches all the way to your brain, your nerves, and a vitamin most doctors never think to check in senior health. The connection between your teeth and vitamin B12 absorption ranks among the most overlooked topics in senior health. And we are going to walk through the science today, step by step, so you understand exactly how it works and what you can do about it. Tooth loss strikes most people as a cosmetic problem, or at worst, a chewing inconvenience. But researchers have uncovered something far more consequential. Losing teeth changes what you eat, how efficiently your body breaks down food, and ultimately, how well you absorb one of the most critical vitamins for your nervous system. That vitamin is B12, also known as cobalamin, and if you are over 60, the stakes are higher than you might expect. A single number sets the stage here, according to the CDC's 2024 Oral Health Surveillance Report, which draws on data from the National Health and Nutrition Examination Survey. Adults aged 65 and older are missing an average of 6.4 teeth. Seniors between 65 and 74 retain about 21.7 teeth on average, and that number drops to 19.8 by age 75 and beyond. Complete tooth loss affects 13.2% of all adults over 65. Those numbers have improved dramatically over the past half-century. Roughly 50% of Americans aged 65 to 74 had no natural teeth at all back in the 1960s. Today, that figure sits around 13%, a 75% relative decline, according to the National Institute of Dental and Craniofacial Research. That is genuine progress. But here is the thing. Roughly 1 in 3 adults over 50 still fall short of what the World Health Organization defines as a functional dentition. The answer starts with how vitamin B12 actually travels from a piece of steak or a fillet of salmon into your bloodstream. Your body runs a 4-step molecular relay. Step 1 takes place in your mouth. Chewing does more than make food small enough to swallow. You are mechanically shearing proteins apart. The answer starts with how vitamin B12 actually travels from a piece of steak or a fillet of salmon into your bloodstream. Your body runs a 4-step molecular relay. Step 1 takes place in your mouth. Chewing does more than make food small enough to swallow. You are mechanically shearing proteins apart and mixing them with saliva, and your saliva contains a protein called haptocorin, also known as R protein, which immediately latches onto any B12 released during chewing. Haptocorin's job is to shield that B12 from being destroyed by stomach acid in the next stage. Step 2 unfolds in the stomach, where hydrochloric acid and an enzyme called pepsin go to work on the food proteins that still have B12 locked inside them. B12 in food clings tightly to animal proteins, and absorption cannot begin until acid and pepsin physically cleave it free. Once released, that B12 binds to the haptocorin. Step 3 plays out in the upper small intestine, the duodenum. Pancreatic enzymes break down the haptocorin, which frees B12 again. And this time it binds to a different protein called intrinsic factor that was secreted by specialized parietal cells in the stomach lining. Step 4 is the final handoff. The intrinsic factor and B12 complex travels to the very end of the small intestine, the terminal ileum, where it docks with a receptor called cubum through a process that requires calcium. Only then does B12 enter your bloodstream. Only then does B12 enter your bloodstream. 4 steps span from mouth to stomach to duodenum to ileum. And here is where the teeth come back into the picture. If step 1 fails, if food never gets adequately broken down by chewing, then the surface area available for acid and pepsin in step 2 shrinks dramatically. Larger food particles mean less enzymatic access. Less enzymatic access means less B12 gets liberated, and less liberation means less of the vitamin reaches the finish line. You might wonder how much chewing efficiency really changes when teeth go missing. The answer, backed by multiple studies, is quite a lot. Research by Gibbs and colleagues, published in the Journal of Prosthetic Dentistry, revealed that adults with moderate loss of posterior tooth support produced a maximum clenching force averaging 462 newtons, compared to roughly 847 newtons in people with full dentition. That translates to a reduction of approximately 258 newtons, or about 58 pounds of biting force, just from moderate posterior loss. Molars carry a disproportionate share of chewing power. Each pair of posterior contacts explains between 10 and 20% of your total bite force variance, which means losing even 1 molar does not simply remove 1/28th of your chewing ability. It disrupts the entire mechanical system. The tooth opposite the gap, now unopposed, tends to drift upward or downward in a process called supraeruption. Adjacent teeth tilt into the empty space, bite alignment shifts, food gets trapped in new crevices, and that domino effect accelerates further loss. For people who have lost all their teeth and wear conventional dentures, the picture grows even more dramatic. Complete denture wearers retain only about 1/5 to 1/4 of the bite strength of someone with natural teeth, according to Gibbs and colleagues in a 1990 study. Comminution tests, where researchers measure how finely people can grind food, tell a similar story. Natural teeth reduced 90% of a test food to small particles, while complete dentures managed only 58%. Masticatory performance in denture wearers ranges from roughly 16 to 50% of what dentate individuals achieve depending on the testing method used. And that brings us to the single most telling study connecting chewing to nutrient absorption. A team led by Rémond at the French National Institute for Agricultural Research published a controlled feeding study in the American Journal of Clinical Nutrition in 2007. 20 elderly volunteers ate a 120-gram beef meal, and the researchers tracked what happened to the protein. Plasma leucine, an amino acid used as a marker for protein digestion, rose more slowly in denture wearers and peaked at lower levels. The headline finding was striking. Postprandial whole-body protein synthesis reached only 30% of leucine intake in denture wearers versus 48% in people with natural teeth, a statistically significant gap. Put plainly, denture wearers extracted roughly 1/3 less usable protein from the same piece of meat. B12 sits locked inside those meat proteins, so the implication follows directly. If you cannot break the protein apart efficiently, you cannot free the B12 trapped inside it. Supporting that conclusion, research by Even and colleagues published in the European Journal of Oral Sciences demonstrated that meat needs to lose roughly 2/3 of its structural strength, dropping from 124 newtons per square centimeter to about 39 before the body considers it ready to swallow. Denture wearers need approximately twice as many chewing strokes to reach that threshold, and even then, they produce coarser food particles with less surface area for digestive enzymes to act on. The mechanical digestion problem, though, represents only one leg of a three-legged problem. The second leg is what researchers call the dietary shift, and it may carry even more weight. When chewing becomes uncomfortable, people stop eating the foods that demand the most effort, and the food that seniors abandon most frequently when they lose teeth is meat. Véroun and Mayoch established that finding in a 2000 study, meat ranks as the single food category most commonly rejected by edentulous older adults. The health professionals' follow-up study tracked nearly 50,000 men, and Joshapura, Willett, and Douglas found that edentulous participants ate fewer vegetables, consumed less fiber and carotene, and took in more saturated fat compared to men retaining 25 or more teeth. Over 9,000 adults from the 2005 to 2008 Haynes cycle were analyzed by Ju and Hollis, who found that adults with 20 or fewer teeth showed significantly reduced intake of protein and most vitamins and minerals. Sayun and colleagues confirmed a similar pattern using Haynes 3 data on nearly 6,000 adults aged 50 and older, showing that impaired dentition tracked with lower healthy eating index scores and reduced fruit and meat and beans intake. The pattern holds up study after study. Lose teeth, avoid meat and hard-to-chew vegetables, consume less B12-rich food. And even the B12 that does get consumed faces less efficient liberation because chewing has been compromised. Which brings us to the third leg. What is happening inside the stomach as you age, regardless of how many teeth remain? A condition called atrophic gastritis, where the stomach lining thins and produces less acid over time, affects roughly 30% of adults over 50, according to a widely cited estimate by Carmel from 1997. A recent Finnish autopsy study published in Age and Aging by Karhunen and colleagues pushed that number even higher, finding atrophic gastritis present in nearly 48% of people over 70. This condition can result from aging alone, but it is also frequently caused by Helicobacter pylori infection, a bacterium that damages the stomach lining over time. Less stomach acid means less pepsin activity, and less pepsin means a diminished ability to cleave B12 from the food proteins it binds to, even if that food was chewed perfectly. Two of the most commonly prescribed medications among seniors layer on top of this problem. Proton pump inhibitors, drugs like omeprazole, esomeprazole, and pantoprazole, deliberately suppress stomach acid production. A study from the Trinity-Ulster cohort, following over 3,000 adults aged 60 and older, found B12 deficiency rates of 38% among those with atrophic gastritis, 21% among proton pump inhibitor users, and 15% in the control group. Metformin, the most widely prescribed type 2 diabetes medication, interferes with B12 absorption by displacing the calcium ions the cubum receptor needs to function in the ileum. Between 10 and 30% of chronic metformin users develop B12 malabsorption, and one study recorded B12 deficiency in over 53% of long-term care residents taking metformin compared to roughly 31 to 33% among non-users. So here is the complete picture. Teeth go missing and chewing force drops. Meat and hard vegetables slowly disappear from the plate. The meat that does get eaten breaks down less efficiently in the mouth. Meanwhile, stomach acid production declines with every passing decade, and medications may suppress what little acid remains. Each of these factors alone poses a problem, but together they create a compounding absorption crisis. The consequences of B12 deficiency are not minor. B12 supports nerve function, red blood cell formation, and DNA synthesis. Deficiency can cause peripheral neuropathy, the tingling and numbness that so many seniors experience in their hands and feet, along with fatigue, weakness, and a specific type of anemia. Through a mechanism involving elevated homocysteine, B12 deficiency has also been linked to cognitive decline and dementia risk. Clinicians often test for B12 deficiency using methylmalonic acid, or MMA, which provides a more sensitive marker than standard B12 blood levels. Clinicians often test for B12 deficiency using methylmalonic acid, or MMA, which provides a more sensitive marker than standard B12 blood levels. A review by Smith and Refsum in the Annual Review of Nutrition documented how B12 deficiency elevates homocysteine, which independently predicts vascular dementia, brain atrophy, and Alzheimer's disease. That connection may help explain a striking finding from dementia research. A 2025 meta-analysis covering 18 cohort studies and over 356,000 participants found tooth loss associated with a 20% increase in dementia risk. The Northern Ireland Prime cohort, also published in 2025, revealed that diet diversity mediated only about 23% of the effect of tooth loss on cognitive impairment, leaving roughly 77% attributable to other mechanisms. B12 status and the homocysteine pathway represent one plausible contributor to that unexplained portion, though researchers caution the link has not been proven directly. If you are watching this and wondering whether dental implants can fix the problem, the answer turns out to be more complicated than the dental industry might suggest. Implant-retained overdentures do substantially recover chewing function, with bite force roughly doubling compared to conventional dentures, going from approximately 162 newtons to 341 newtons, and the number of chewing strokes needed to break down food dropping significantly. But here is what surprised researchers. A well-designed randomized controlled trial by Hamdan and colleagues, published in the Journal of Dental Research in 2013 with 217 participants, found that implant overdentures did not improve 24-hour dietary intake compared to conventional dentures after 1 year. Better chewing ability alone did not change what people chose to eat. Decades of dietary habits did not automatically reset when participants received new teeth. Evidence now consistently shows that dental rehabilitation must pair with nutrition counseling to actually improve nutritional status. So what should you do with all of this? The most practical step comes first. If you are over 50, the American Academy of Family Physicians recommends meeting your B12 needs through fortified foods or supplements. If you are over 50, the American Academy of Family Physicians recommends meeting your B12 needs through fortified foods or supplements. This matters because crystalline B12, the form found in supplements and fortified foods, does not require stomach acid to be absorbed. It bypasses the entire food protein liberation step we have been discussing. If you have lost teeth, focusing on B12-rich foods that are easier to chew makes a real difference. Eggs, soft fish, dairy products, and ground meat all deliver B12 without requiring the same chewing force as a steak or a pork chop. Consider the broader pattern as well. If your diet has shifted over the years toward fewer vegetables, less meat, and more soft processed foods, ask yourself whether dental problems might be driving that change. Medicare has excluded routine dental care since 1965. Recent rules in 2023, 2024, and 2025 expanded coverage only for dental services that are, in the government's language, inextricably linked to a covered medical procedure. About 56% of adults 65 and older carry no dental benefits at all, according to the American Dental Association. Without coverage, a single dental implant averages around $3,100 to $5,800, and a full set of conventional dentures runs $1,000 to $3,000 per arch. Let us bring this full circle. The connection between your teeth and your B12 status is not a simple, one-step mechanism. It operates as a web of reinforcing factors. Tooth loss reduces chewing force, and reduced chewing force produces coarser food particles with less surface area for digestive enzymes. At the same time, tooth loss drives a dietary shift away from the very foods that contain B12. Aging independently reduces the stomach acid needed to liberate B12 from food, and common medications magnify that decline. Each factor alone is manageable, but together they create a compounding risk that can quietly erode your B12 status over years, potentially contributing to nerve damage, anemia, and cognitive decline. The most actionable takeaway from all of this research is that tooth loss is a flag, not a final sentence. Crystalline B12 supplements bypass the problem. Understanding the connection is the first step. If you found this information useful, please subscribe and share this video. This content is for educational purposes only. Please consult your healthcare provider.